1933. Workers began building the Golden Gate Bridge in January. By May 1937, 52 months later, it was finished, ahead of schedule, under budget. Today, in 2024, the San Francisco-Oakland Bay Bridge, Eastern Span, replacement took 24 years from earthquake damage to opening. The modern bridge cost $6.5 billion, rising to over $12 billion with financing. It opened 6 years late with broken safety bolts. This is one of the cables they spun in 1935. October 1935, spinning wheel carriages race across the 4,200-foot gap, pulling silver wire at 650 feet per minute. Workers on catwalks position each wire by hand while standing 400 feet above water, so black from churning tides you cannot see through it. By day's end, 1,000 miles of wire have been added to the cables. 1933 to 1937, 52 months, the longest suspension bridge in the world. Today, in 2024, the Bay Bridge Eastern Span took 24 years, 288 months, more than 5 times longer. The first proof came in February 1933, just 2 months after construction began. The anchorage blocks were complete, each one 60,000 tons of concrete, 12 stories tall, 6 above ground, 6 below, built in a San Francisco winter in 8 weeks. Workers poured 120 cubic yards per hour, approximately 12 concrete mixer trucks worth every hour, hour after hour, day after day. These structures would hold 63 million pounds of cable tension for the next 100 years. Any flaw would doom the entire bridge. They finished both anchorages in 2 months. The Golden Gate Strait was not a construction site. It was a grinding machine. 2.3 million cubic feet of water per second, 1/6 of the entire San Francisco Bay, flowing in and out daily, forever. The strait had been churning for millions of years. It would destroy any human structure placed in its path. 1,000 miles of wire per 8-hour shift. That's 125 miles per hour. Over 2 miles of wire per minute being pulled across a windswept channel while workers positioned each strand by hand. No computers, no GPS, radio coordination, and human precision. In 1933, they built the longest suspension bridge in the world in 52 months. 11 men died. Today, in 2024, we have better tools, better materials, better safety equipment. We can no longer build at their speed. This is the story of what we gained and what we lost. That was the speed. Now here's what they were fighting. The Golden Gate Strait, where the Pacific Ocean meets San Francisco Bay, is one of the most violent bodies of water in North America. The bridge had to cross it, and the strait was not going to make it easy. But completing the anchorages in 2 months was only the beginning. The real challenge, the piece that engineers said was impossible, was 1,125 feet offshore. Engineers in the 1920s said a bridge across the Golden Gate was impossible. Not difficult. Impossible. The strait was too wide, too deep, too violent. Water depth at the channel center, 372 feet. Tidal, currents, powerful enough to move 2.3 million cubic feet of water per second. Wind, fog, earthquakes, the San Andreas Fault just 7 miles offshore, and the South Tower, the critical support, had to be built 1,125 feet offshore in the middle of all this violence. Workers called them highwaymen, the iron workers who worked at the highest elevations, 800 feet in the air, atop the towers, on the cables stretched between them. Not criminals, the opposite. These were the most skilled workers, the most fearless, the most expensive. Working at extreme heights was prestigious. A highwayman earned top wages, sometimes $11 per day when common laborers earned $4. But you had to earn the position. One mistake at 746 feet, and you were dead. The cable spinning began in October 1935. The target seemed impossible. 80,000 miles of wire, enough to circle Earth 3 times, to be spun into 2 cables. The Roebling Company had spun cables for the Brooklyn Bridge in 1883 and the George Washington Bridge in 1931. They knew the technique, but they had never moved this fast. 4 spinning wheel carriages launched simultaneously across the span at 650 feet per minute. Each carriage pulled 6 wires, back and forth, back and forth. Workers positioned each wire by hand into geometric patterns calculated by Charles Ellis. Radio transmissions coordinated tension adjustments between shores. The speed was relentless, 271 tons of wire per day per cable. The George Washington Bridge, finished just 4 years earlier, had achieved 61 tons per day. The Golden Gate crews were 4.4 times faster. In 191 days, the job was done. 80,000 miles of wire, 27,572 wires per cable, every one positioned by hand. February 1933, both anchorages complete. 8 weeks of work, 120,000 tons of concrete total. Today, a 12-story concrete building typically takes 18 to 36 months to complete. We have better concrete, better pumps, better forms. We take 9 to 18 times longer, but speed wasn't the challenge. The challenge was the strait itself, 2.3 million cubic feet of water per second. The strait was not waiting for mistakes. It was looking for them. The assumption, the highest elevations were most dangerous. The reality, 0 deaths from falls from the 746-foot tower tops. The most experienced workers, the highwaymen working at extreme heights, all survived. They understood the danger intimately. They took precautions. The deadly height was moderate elevation, where the safety net created false security. On February 17, 1937, a scaffold at approximately 200 feet fell. Undersized bolts failed. The scaffold broke through the net. 10 men died. The obvious danger at extreme heights killed no one. The hidden danger in the equipment killed 10. The South Pier had to be built 1,125 feet offshore in water, 372 feet deep. Before construction could start, divers had to blast foundation wells into bedrock at 90 feet depth. The water was completely black. Sediment churned by 2.3 million cubic feet of water per second made visibility 0. Divers descended in canvas suits with brass helmets. They worked by feel. They couldn't see their own hands. Each dive was timed to slack tide, the brief period between flood and ebb when currents weakened. They had 75 minutes maximum. At 90 feet, decompression concerns limited bottom time to 20 minutes. In complete darkness, working by touch, they positioned 6 bombs containing 200 pounds of dynamite. They signaled completion. They surfaced. The charges detonated underwater, visible from shore. Then another diver descended to survey the blast and position the next charges. In 1933, blind, in violent currents, they blasted bedrock at the bottom of the Pacific Ocean. The workers who fell into the safety net and survived called themselves the Halfway to Hell Club. 19 men total. They'd gone over the edge, started the fall that should have killed them, and the net caught them 60 feet below. Halfway to hell. They wore the name with pride. Some even posed for photographs in the net. The club became famous. People tried to jump into the net on purpose just to join, which had to be forbidden. Dark humor about mortal danger. But the humor stopped on February 17, 1937. The towers went up throughout 1934 and 1935. Each tower, 746 feet tall, constructed from 404 steel cells, held together with 600,000 rivets. Rivet gangs worked hundreds of feet above the water in constant wind. The heater warmed rivets over a coal fire until they glowed red. He threw the rivet across a gap, maybe 6 feet, where the catcher caught it in a bucket. The bucker positioned the hot rivet. The gunman drove the pneumatic hammer, forming the second head while the metal was still hot. Dozens of rivets per hour. The towers had to taper precisely from 33 by 54 feet at base to 11 by 25 feet at top. Any error at 200 feet would be magnified by 746 feet. They had transits and levels, no lasers, no GPS. The North Tower was completed in May 1934, the South Tower in January 1935. Both towers perfectly vertical, precisely positioned, ready to hold cables weighing 6,100 tons. 1935-1936, cable spinning complete in 191 days. 271 tons of wire per day. Today, modern cable installation on major bridges takes years despite computer-aided design, advanced materials, and automated tension monitoring systems. We have better tools. We move slower. Divers could set charges, but divers couldn't build a pier in the middle of violent currents. The solution was unprecedented, and it cost a fortune in temporary infrastructure that would be abandoned once the pier was built. The weapon was the fender, what workers called the giant bathtub. 130,000 tons of concrete built in a circle around the South Pier location, 1,125 feet offshore, roughly the size of a football field. The fender was not part of the bridge. It was built just to protect the worksite from the strait. Once the fender was complete and sealed, workers pumped out millions of gallons of seawater. Day after day, pumps ran continuously. The water level inside the fender dropped foot by foot, exposing bedrock that had been underwater for millions of years. When the pumping was done, workers stood at the bottom of the Pacific Ocean in a dry pit. They built the pier, using conventional land-based construction methods, inside a fortress that held back the strait. The fender cost a fortune. It would be abandoned once the pier was complete, but without it, the pier was impossible. So they built a temporary structure that weighed more than 13,000 cars just to create a dry work area for a few months. Then they pumped out the ocean. 52 months, January 1933 to May 1937. They moved 3.25 million cubic feet of earth. They poured 388,500 cubic yards of concrete. They erected 2 towers, 746 feet tall. They spun 80,000 miles of wire. They installed 250 pairs of suspender ropes. They built a bridge, the longest suspension bridge in the world. 52 months. Today we spend 52 months writing environmental impact statements. The assumption, old means slow. Primitive technology means tedious progress. The reality, the Golden Gate cable spinning in 1935-1936 was 4.4 times faster than the George Washington Bridge completed in 1931 using essentially the same technology. Same basic spinning wheels, same wire, same technique. But the Golden Gate achieved 271 tons per day while the George Washington managed 61 tons. This wasn't primitive. This was refined technique pushed to maximum speed by organizational will. Technological capability doesn't always progress linearly. Sometimes old systems, refined through experience and pushed by skilled workers and relentless management, achieve results that modern technology cannot match. The fender solved the physics problem. They'd beaten the strait. But solving engineering problems was the easy part. The hard part was making thousands of decisions, fast enough to maintain 52-month timeline with hundreds of workers, multiple contractors, supply chains, weather, accidents, and a Depression-era workforce, desperate for any job. That required a management structure we no longer use. Joseph Strauss, Chief Engineer. Born 1870. Graduated University of Cincinnati, 1892, with a civil engineering degree. By 1933, he'd built 400 bridges across the United States and internationally. His resume was impressive, but there was a problem. Every single one of those 400 bridges was a bascule bridge, a drawbridge. The Golden Gate Bridge was Joseph Strauss's first suspension bridge. He'd never built one before. The actual structural engineering, the deflection theory calculations, The stress analysis, the cable sizing, was done by Charles Alton Ellis, a professor at the University of Michigan. During the Depression, to save consulting fees, Strauss fired Ellis. Ellis was not recognized when the bridge opened in 1937. Whether Ellis ever saw the completed bridge is unknown. He died in 1949. In 2012, 75 years after opening, a plaque acknowledging Ellis's contributions was finally installed. The South Pier was the hardest piece. It had to be built 1,125 feet offshore, where 2.3 million cubic feet of water per second flowed past during tidal exchange. The solution was the fender. Workers called it the giant bathtub. 130,000 tons of concrete built in a circle around the pier site, roughly the size of a football field. The fender extended from seafloor to above water level. Once complete, pumps began removing water. Day after day, millions of gallons. The water level dropped foot by foot. Finally, bedrock emerged, rock that had been underwater for millions of years. Fish flopped on the suddenly dry surface. Workers held an impromptu fish fry. Then they began building the pier in a dry excavation at the bottom of the Pacific Ocean. The fender cost a fortune. It was temporary, abandoned once the pier was complete. But without it, the pier was impossible. So they built a 130,000-ton temporary structure just to create a dry work area. 1934, divers worked blind in black water for 20 minutes at depth. No visibility, canvas suits, brass helmets. They set charges and blasted bedrock. Today, we have sonar, underwater cameras, advanced breathing systems. But before any diver enters the water, we need months of permitting, safety reviews, environmental assessments, marine mammal monitoring plans. The technology got better. The timeline got worse. Workers called the concrete delivery system the elephant trunk, a long, flexible tube that snaked down into the excavation pits, sometimes 60 feet deep. The trunk delivered 120 cubic yards of concrete per hour. Workers stood in the pits while concrete flowed down to their level. They guided the flow, ensured proper consolidation, built upward continuously. The playful name, elephant trunk, contrasted with the brutal reality. Standing in a pit 6 stories below ground level, while tons of wet concrete poured down around you. If something went wrong, if you couldn't get out, the concrete would bury you. But workers gave it a cartoon name. This was how they coped. Great projects often succeed despite their organizational structure, not because of it. But workers weren't moving this fast because they loved their jobs. They were moving this fast because the alternative was starvation. This was 1933, the Great Depression. 1 in 4 Americans had no work. Men waited at the base of towers for workers to fall so positions would open. June 1936. The cables are complete now. Massive, compressed, wrapped, painted international orange. Stand on the South Tower at 746 feet elevation and look down at the cable curving away from you in both directions. It's a perfect catenary, the shape that distributes load most efficiently, calculated by Charles Ellis without computers. The cable is over 3 feet in diameter, heavier than a locomotive, stronger than anything built before. Workers in bosun's chairs, rope seats like swings, dangle from the cable, installing the vertical suspender ropes that will hold the roadway. Below them, 400 feet down to the water. Above them, only sky. The cable thrums with tension under your hand. You can feel it vibrate in the wind. This isn't a static object. It's alive, flexing with every gust, absorbing forces and distributing them to the towers and anchorages. Beneath the orange paint wrapping are 61 strands. Beneath each strand are 452 wires, 27,572 total wires, each positioned by hand, each carrying its share of 6,100 tons of load. Every wire is doing its job. Look across the span. The twin cables mirror each other perfectly. Between them, roadway sections are being lifted into position, hanging like a massive hammock. In a year, 280,000 vehicles will cross daily. For now, workers crawl over every surface, finishing what cannot be finished on the ground. In June 1936, Strauss did something unprecedented. He installed a safety net beneath the entire bridge at a cost of over $130,000. This when workers earned $4 to $11 per day. The rule of thumb in 1930s construction was one death per $1 million spent. For a $35 million project, 35 deaths were expected. Strauss rejected this. The net was suspended 60 feet below the workers, designed to catch falling men without killing them on impact. It worked. Over the course of construction, 19 men fell into the net and survived. They formed the Halfway to Hell Club, men who'd gone over the edge and lived. The net gave workers confidence to move faster. It became famous. People tried to jump into it on purpose, which had to be forbidden. On February 17, 1937, a scaffold weighing many tons fell and broke through the net, killing 10 men. But for most of construction, the net saved every man who fell. It was innovation born from refusing to accept that death was the price of speed. June 1936, Strauss decided to install the safety net. Cost over $130,000 in Depression dollars. A completely novel system never used before on a bridge. Implementation timeline: months. Today, implementing a major safety innovation requires engineering studies, contractor approvals, insurance reviews, regulatory submissions, competitive bidding. Timeline: 1 to 2 years from decision to installation. The fender was called the Giant Bathtub by everyone on site. The name fit. 130,000 tons of concrete built in a circle 1,125 feet offshore, roughly the size of a football field. Its job was to keep water out, like a bathtub, but inverted. Once the bathtub was built and sealed, pumps removed millions of gallons of seawater. The water level inside dropped until bedrock, underwater for millions of years, was exposed. Workers could then build the pier in a dry pit at the bottom of the Pacific Ocean. The casual name, Giant Bathtub, made it sound simple. It wasn't. It was one of the most difficult pieces of engineering in the entire project. Modern safety regulations would have saved some of the 11 men who died. But would the bridge have been built at all? The safety net, which saved 19 lives, wouldn't meet modern OSHA standards requiring personal fall arrest systems for each worker. The bolts that failed could have been caught by modern engineering review, but similar failures still occur. Here's the trade-off. The Golden Gate Bridge. 11 deaths in 52 months of construction, but the bridge was built. The Bay Bridge Eastern Span. 0 construction deaths in 11 years of construction, but residents crossed a seismically unsafe bridge for 24 years while we reviewed, studied, and delayed repairs. Fewer construction workers died, but how many people were at risk crossing an earthquake-damaged bridge for 2 decades? The trade-off between speed and safety is real, complex, and doesn't have an obvious correct answer. Once the main cables were complete, workers had to install 250 pairs of vertical suspender ropes to hold the roadway, each rope over 2.5 inches in diameter. Each one had to be cut to precise length because the curve of the main cable varied along the span. Workers sat in bosun's chairs, rope seats, like swings, attached to the main cable 400 feet above the water. Wind whipped constantly. They measured, cut, and attached each suspender rope by hand, ensuring exact 50-foot spacing. Once the rope was attached to the cable above, they climbed down to attach the bottom to the roadway section being positioned below. This process was repeated 500 times along the bridge's length. Below them, water. Above them, sky. In their hands, the ropes that would carry millions of vehicles. No fall arrest systems. No rescue plans beyond hope. Just workers in rope seats, building a bridge. That was the organizational machine. Ruthlessly efficient. Relentlessly fast. But it ran on human fuel. And humans are not machines. They bleed. They fall. They die. The safety net saved 19 lives, but it couldn't save everyone. February 17th, 1937. The net saved 19 lives, but on February 17th, 1937, the net failed. What nobody talks about is what failed first. Not the net, but the bolts. The Golden Gate Strait in winter. Wind whipping through the towers. Workers insulated their jackets with crumpled newspaper because that's all they had. Martin Adams, an iron worker, later described it. You put all the clothes on you had and worked hard, or you'd freeze. He called the Golden Gate Strait the coldest place I've ever worked. Workers faced Pacific winds at 746 feet elevation with no shelter, 8-hour shifts with minimal breaks, cold that numbed fingers, making it difficult to grip tools and cables. Men worked through injuries that would hospitalize them today. They worked in fog so dense they couldn't see 10 feet. They worked because the alternative was unemployment and starvation. This was 1933. The Depression. 1 in 4 Americans had no job. February 17, 1937. Slim Lambert was on the scaffold with 11 other men, removing temporary wooden structures. The scaffold was secured by undersized bolts. The bolts failed. Lambert felt the platform drop. The only thing that went through my mind was survival, he later said. I knew that to have a prayer I had to hit the water feet first. He fell 200 feet. He hit the water. His legs tangled in the safety net, which was sinking. The net pulled him deep. So deep his ears bled from the pressure. He fought free of the net underwater, swam to the surface. A crab fisherman pulled him and 2 others from the water. 1 died shortly after. Lambert and Oscar Osberg survived. 10 men didn't. Lambert had been a member of the Halfway to Hell Club, men who'd fallen into the net and survived. On February 17, 1937, the net couldn't save him. He had to save himself. August 1933, cargo vessel destroys access trestle in fog. Response, repair crews mobilize in days. Other work continues. Trestle rebuilt in 10 months. Today, a similar accident would trigger comprehensive safety review, accident investigation, litigation holds, insurance claims processing, revised safety plans, regulatory submissions. All work halted. Timeline, 18 months to 2 years before full work resumes. Rivet gangs called their work driving steel or punching rivets. 4 men worked as one unit. The heater warmed rivets to glowing red over a coal fire. The catcher positioned himself across a gap, maybe 6 feet, maybe 10, and waited. The heater threw the glowing rivet. The catcher caught it in a bucket. The bucker positioned the hot rivet in a drilled hole. The gunman drove the pneumatic hammer, forming the second head while the metal was still hot. The rhythm never stopped. Heat, throw, catch, buck, drive. Heat, throw, catch, buck, drive. Dozens per hour, hundreds per day, 600,000 per tower. The rivet gangs built the towers 1 hot rivet at a time, hundreds of feet above the water. The most expensive single element wasn't steel or cable wire, it was the fender. 130,000 tons of concrete built offshore just to create a dry work area. The fender was not part of the bridge. It was temporary infrastructure built to build infrastructure. Once the South Pier was complete, the fender was abandoned, left in place, or demolished. The safety net cost over $130,000 in Depression dollars. enough to pay the entire workforce for weeks. Also temporary. These costs are invisible to the public. Nobody photographs the fender. Nobody remembers the scaffolding, the elephant trunk concrete delivery systems, the concrete plant Strauss built just for quality control. But these temporary works consumed massive resources. A huge portion of infrastructure cost is invisible infrastructure to build the visible infrastructure. Kermit Moore, October 21, 1936, crushed by a falling beam. First death after nearly 3 years with 0 fatalities. Then, February 17, 1937, 10 men on a scaffold. Undersized bolts. The scaffold fell. It broke through the net. 200 feet down to the water. Slim Lambert survived. His ears bled from being pulled so deep by the sinking net. Oscar Osberg survived. 10 men didn't. Their names are recorded. History remembers them. But history doesn't remember what happened to their families, who paid for the funerals, how their widows survived. History remembers the bridge. The men are footnotes. Charles Kring was cable supervisor during the spinning operations in 1935-1936. His crews were achieving 271 tons of wire per day, unprecedented speed. Kring later recalled what he witnessed at ground level. Men waited at the base of the towers, watching, waiting, hoping someone would fall. Not out of malice, out of desperation. There was always somebody waiting at the base of the tower for someone to fall off so they'd get a job, Kring said. This was the Depression. 1 in 4 Americans had no work. A job on the Golden Gate Bridge paid $4 to $11 per day. Fortune in 1933. Men were willing to take positions that had just killed someone because the alternative was starvation. Kring watched this desperation every day while his crews spun wire hundreds of feet above. The speed wasn't just engineering. It was desperation made productive. 11 deaths in 52 months. By the standards of 1937, this was remarkable safety. Today, we would shut down the project, and that's exactly what we've done. Not literally, but effectively. Since 1970, we've built a system that prevents deaths by preventing construction. 1933, decision authority rested with Strauss and Cohn. Foreman made immediate changes. Major decisions needed only Strauss's sign-off. Strauss was on site nearly every day. Today, the Bay Bridge Eastern Span required approvals from Caltrans Management, Metropolitan Transportation Commission, Toll Bridge Oversight Committee, Seismic Safety Review Boards, Environmental Compliance Agencies, Legislative Oversight Committees. A design change requiring Strauss's signature in 1933 would require sign-offs from 8 to 15 entities in 2024. Martin Adams was a highwayman, one of the iron workers at extreme elevations. He worked atop the towers and on the cables. On February 17, 1937, he was working at height when the scaffold collapsed. He watched it fall. He watched it break through the net. He watched 12 men drop 200 feet. 10 died. Adams later described the working conditions at height. You put all the clothes on you had and worked hard, or you'd freeze. Workers facing Pacific winds atop the 746-foot towers insulated their jackets with crumpled newspaper to survive. The coldest place I've ever worked, Adams said about the Golden Gate Strait. He survived 4 years of construction at the most dangerous positions. He witnessed the worst accident. He kept working. The bridge opened 3 months later. Adams had helped build it. He'd watched friends die building it. He lived to see it completed. 11 deaths in 52 months. The workers deserved better. They absolutely deserved better. And today we've built a system that protects workers. 0 construction deaths on the Bay Bridge Eastern Span in 11 years of construction. But here's what we don't talk about. The cost of that protection isn't just money. It's time. And time has consequences. We don't build like 1933 anymore. That's a good thing. The workers of the Golden Gate Bridge deserved better. They deserved modern safety equipment. They deserved fall arrest systems. They deserved engineering reviews that would catch undersized bolts before 10 men died. They deserved not to work in conditions so cold they stuffed newspapers in their jackets. They deserved not to wait at tower bases hoping someone would fall, so they could have a job. We were right to create OSHA in 1970. We were right to create environmental protection laws. The rivers should not catch fire. The neighborhoods should not be bulldozed without community input. This is moral progress. The Bay Bridge Eastern Span took 24 years and $6.5 billion with 0 construction deaths. This sounds like progress, but there's a date when everything changed, when we decided process mattered more than outcome. January 1st, 1970, the National Environmental Policy Act, signed into law by President Richard Nixon on January 1st, 1970, created by Senator Henry Scoop Jackson from Washington State. NEPA required federal agencies to assess environmental impacts before taking action, write environmental impact statements, evaluate alternatives, engage the public. This was necessary. Rivers were catching fire. Highways were bulldozing neighborhoods. Air was poisonous. NEPA said, stop, think, consider the consequences. But here's what happened. Before January 1st, 1970, an engineer could propose a bridge, secure approvals, win funding, and begin construction. Joseph Strauss spent 1919 to 1930 campaigning, securing military approval, addressing concerns, winning voter approval. Once voters approved bonds in November 1930, construction began January 1933, 26 months from approval to start. After January 1st, 1970, major infrastructure projects require environmental impact statements before construction begins. The average EIS takes 4.5 years to complete. By 1975, just 5 years after NEPA, the Army Corps of Engineers reported the law had caused modifications, delays, or halts in 350 of its projects. The Bay Bridge Eastern Span. Earthquake damage. October 1989. Construction begins 2002. 13 years of planning and review before construction could start. The planning phase alone took 3 times longer than the entire Golden Gate Bridge construction. 1937. Golden Gate Bridge final cost, $35 million under budget. In 2024 dollars, approximately $700 million 2013. Bay Bridge Eastern Span final cost, $6.5 billion direct construction, over $12 billion with financing. Approximately 17 times more expensive per mile when adjusted for inflation. We didn't just get slower, we got exponentially more expensive. Environmental impact statement, 4.5 years average. Public comment period, 6 to 12 months. Legal challenges, 1 to 3 years if they occur. Permit coordination across multiple agencies, 1 to 2 years. Total pre-construction timeline, 7 to 10 years. For major projects, sometimes longer. The Bay Bridge Eastern Span, 13 years from earthquake damage to construction start. Just to start, not to finish, to start. We don't build slowly, we delay indefinitely. The Golden Gate Bridge is not golden, it's orange. International orange, specifically. Residents expected or feared the bridge would be gray, black, brown, or golden. But during construction, the steel was coated with orange primer for weather protection. Consulting architect Irving Morrow saw the primer during construction and thought the warm tone suited the location perfectly, contrasting with blue water and sky, visible in famous San Francisco fog. He recommended making the temporary primer color permanent. The most photographed and iconic aspect of the Golden Gate Bridge, the feature that makes it instantly recognizable worldwide, was essentially a construction accident. Sometimes the best design decisions happen during construction, not during planning. The planning process never would have approved orange, but once workers accidentally painted it orange as primer, it was obviously correct. When a worker fell, other workers said he made a drop or took a fall. Casual language for mortal danger. Making a drop sounds like making a trip to the store. Taking a fall sounds like tripping on a sidewalk. This linguistic distancing helped workers cope with the constant fear. Before June 1936, before the safety net, making a drop meant death. After the net was installed, it meant survival. 19 men made drops and lived, but the language stayed casual. On February 17, 1937, when the scaffold fell and broke through the net, 10 men made their final drop. The euphemism couldn't protect them. November 1930, voters approve bonds. January 1933, construction begins. Elapsed time, 26 months. Most of this was financing and design, not environmental review. The Bay Bridge, Eastern Span, earthquake damage, October 1989. Construction begins 2002. Elapsed time, 13 years, 156 months, 6 times longer just to start construction. The planning phase alone took 3 times longer than the entire Golden Gate Bridge construction. But we face deadlines. Climate change requires infrastructure transformation. Aging bridges need replacement before catastrophic failure. Electrical grids need modernization. Water systems need upgrading. Housing crises need solutions. These are not abstract problems. They have human costs. The Bay Bridge Eastern Span was seismically unsafe after 1989. Residents crossed it daily for 24 years while we reviewed and studied and delayed. How many people were at risk? How many would have died if a major earthquake hit during those 24 years? We optimized for 0 construction deaths. We accepted the risk of catastrophic public deaths. This is the uncomfortable question. When does protection become paralysis? When does careful become catastrophic? Is there a way to build fast and safe? What would it require? Except that some risk exists. 0 risk is impossible. Streamline approval processes without eliminating environmental review. Allow competent authorities to make binding decisions. Use modern technology to accelerate, not just to analyze. Parallel process reviews instead of sequential. Set hard deadlines for regulatory decisions. Accept that perfect review is the enemy of necessary construction. The Golden Gate Bridge killed 11 workers. That's 11 too many. But it was built. The Bay Bridge Eastern Span killed 0 construction workers. But it took 24 years and left residents at risk for decades. There must be a middle ground. We haven't found it. We haven't seriously looked for it, because looking for it requires admitting we've overcorrected. 1937. Golden Gate Bridge opens, 2024, still functioning perfectly. 87 years, 112,000 vehicles daily, routine maintenance only. The original cables spun in 1935 still carry traffic. 2013, Bay Bridge Eastern Span opens. 2015, major repairs needed for cracked bolts, questionable welds, corrosion concerns. The bridge we built with primitive 1930s technology has worked flawlessly for 87 years. The bridge we built with advanced 2010s technology had serious structural problems within 2 years. So here we are, in 2024, with better tools than 1933, better materials, better safety equipment, better computers, better everything, except one thing: the organizational will to move fast. That cable spun in 1935 is still there, still working, outlasting everyone who built it. Better tools, better materials, better computers, better safety equipment, better everything, except speed, except will, except the capacity to move fast when the situation demands it. We know how they did it in 1933. We have the historical records. We have the engineering drawings. We have photographs. We have survivors' oral histories. We know exactly how. But we cannot do it again. Not because we lack the technology, because we lack the will. So what do? Accept that building slowly with 0 risk is worth decades of delay? Or rediscover the organizational will to move fast while managing, not eliminating, risk? The workers of 1933 deserved better, but the residents of 2024 deserve better too. They deserve bridges that don't take 24 years. They deserve infrastructure that gets built before crisis becomes catastrophe. They deserve a society that can still build monuments. The question is not whether we should go back to 1933 safety standards. We shouldn't. The question is whether we can rediscover 1933 speed with 2024 safety, or whether we've permanently traded capability for caution. The Golden Gate Bridge stands. The men who built it are gone. The organizational will that pushed them to move that fast is gone. Can we build it again? Or have we chosen not to? The cable is 87 years old now. Stand at Fort Point and look up at the South Tower. The cable curves overhead, painted the same international orange, flexed by the same Pacific winds. Painters work year-round, maintaining the color, fighting corrosion. The wrapping wire shows age despite constant maintenance, but inside, the 27,572 core wires spun in October 1935, the steel remains sound. Engineers have inspected, X-rayed, analyzed these cables for decades. The wires still work. Joseph Strauss died in 1938. Charles Ellis died in 1949 without recognition. The Halfway to Hell Club members are all gone. The 10 men who died when the scaffold fell through the net in February 1937 have been forgotten by everyone except historians. The cable remembers nothing. It just works, carrying 112,000 vehicles daily, flexing up to 27 feet in high winds, aging slowly, but not failing. Somewhere deep inside this 3-foot spiral of steel are wires touched by men whose names nobody remembers. Their hands positioned these wires with radio coordination and manual precision in 1935. They've been dead for 50, 60, 70 years. The cable they built still works perfectly. That's what they left behind. Not their names, but the wires. The bridge will likely outlast everyone reading this. It will carry traffic into the 22nd century. The cables spun in 1935 will still flex in Pacific winds in 2100, 2120, 2150. The workers will be forgotten. The Halfway to Hell Club will be a historical curiosity. The 11 deaths will be statistics. But the bridge will remain, working, carrying traffic, proving something that we've chosen to forget, that humans once built things this big, this fast, this well. The bridge is the evidence. The only question is whether anyone will remember what it proves.